All right, we've gone through our PT, we've gone through our refrigeration cycle, we've covered compressors, we've covered our condenser, right? Now we've got this liquid coming out of here, and we are now ready to start talking about metering devices. Let's talk about the metering device. On our regular refrigeration, our little super simple refrigeration cycle, okay, we hit that metering device and we just kind of go through that into the evaporator, right? In our world, there's a lot going on here. This is one of the most critical pieces of our entire refrigeration system, all right? So we're going to break it down, not into baby steps, but we are going to break down the key components that as a technician we need to understand. Okay, not going to go into a ton of theory here. We will cover the correction factors. We will make sure we understand that pretty well. All right, so before I start talking about my metering device, there are 3 liquid conditions that we must meet in order for our device to work properly. All right, now you guys, this is the first time in any of my slides you have seen me put words that are not titles. Right? Everything so far has been pictures over there. Now you're getting words.
Bring back pictures.
Think this might be important?
Yeah, apprentices only.
All right. First one, the solid column.
Yes, sir.
Before I take a superheat on anything, I must ensure that I have a full pipe full of liquid feeding that expansion device. All right? Doesn't matter what device it is. It must have a full pipe of liquid. When we say solid column, that's what we mean. No vapor, no non-condensables, 100% liquid into that valve. If I can't guarantee that, taking superheat is a waste of time. Means nothing, right? The value that I'm going to get when I take my superheat is meaningless. All right? Subcooled. No matter what system I have, no matter what type of mechanical subcooler or not I have, that liquid must be subcooled before it hits that valve, or cap tube, or expansion device, whatever. Must be subcooled. Now, it doesn't have to be subcooled much for it to work, to function, but it must have subcooling. It cannot be at saturation. Right? It must be below saturation. Even if it's 1/10 of a degree, it must be below saturation. In the supermarket world, in our supermarket cases, it's got to be a lot lower than that. It's got to be significantly lower than that. Right? On stores that don't have subcoolers, mechanical subcoolers, they do have heat exchangers at the cases, right? Why do you think that is? To guarantee that I've got some subcooling.
Also, why they run a liquid line through the
That's it.
drain.
Right, liquid line soldered to the suction line. Right, we see that too, if there's no mechanical subcooler. What's that doing? All that's doing is ensuring my liquid is subcooled, okay? All right? Second thing I must have, I have to have that pressure differential that we were talking about. The difference between my suction and my discharge pressure has to be high enough for that valve to work. All right? Where we run into problems with this, that liquid holdback or valve that we just covered, right? In hot gas defrost, or my quote 15-pound differential valve, that thing is 30 pound, 40 pound, 50 pound, starts getting off, right? Right here, I could have a real problem, okay? So before we do anything, anytime you're talking to me on the phone and you got a problem, right? I'm gonna ask you these 3 questions. These are your fundamentals. Before you get your temperature gauge out, before you get your fancy probe out, start screwing it on to take suction pressure, before you do anything, confirm that these 3 things are good to that case. That's running warm, right? That's why you're there, it's running warm. Okay? Fundamentals that must happen. All right, that's the last time you're gonna see words over there. First and last in this entire course. That is incredibly important, right? And easy to miss. Easy to get caught in the moment of a case running warm and you're trying to figure out everything out. Right? Super important. Okay, so in our world, when we're talking about a metering device, the most common metering device that we have is the thermal expansion valve. Okay? So TXV, thermal expansion, TEV, right? Interchangeable, they mean the same thing. It's literally geographic. You know, when you start going up north, you might hear TEV more than down here. TXV is pretty common down here. Whatever, they're the same thing. We're talking about a valve that causes that refrigerant to expand, go from high pressure to low pressure, right? Based on a temperature, thermal. That's the thermal piece, okay? So when we talk about, when I started this whole course, I started talking about direct expansion and said all direct expansion devices work this way. This is where the expansion's happening. This is the expansion, all right? This is what's going to cause my refrigeration effect. This is the key to this entire thing working, all right? This is going to be the difference between my high pressure and low pressure system. That change happens in this valve. Everything coming in is high pressure, everything going out is low. Right? So yeah, it's kind of important.
They don't charge enough for those valves.
Should charge more, they're pretty important.
No, we should charge more, they should charge less. We should be able to pick one up for like 50.
Well, that's thinking like a businessman.
Yeah.
All right, how many of these we got in the store?
Hundreds.
Literally hundreds.
Yeah.
Literally hundreds, right? You take the new Husband 4-foot lineups, each one's got its own valve. We got more than one per case in some situations, right? Yeah, we got a gazillion of these things. All right, the other thing this guy is responsible for, he has the sole responsibility for superheat of my rack. Right? We know it impacts superheat of my rack, but did you catch what I said before that? Sole responsibility.
Yep, it's the only thing.
There is nothing on my rack that will cause my superheat to be too high or too low that is not a metering device. Yeah, let that sink in, think about it, and pop questions to me if you need to, right? Yeah, changing my EPR doesn't got nothing to do with superheat. Just doesn't. Right? Changing my whole back valve's got nothing to do with superheat. Right? This guy controls that. Right? So since I've got hundreds, what am I reading on my rack? If I go to my rack and I'm reading the superheat of my rack, am I reading this valve?
Yeah.
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 And all of his brothers.
Yeah.
Right? It's going to give me an average. If I have one valve, just one of those 100, flooding, will that liquid make it back to my rack?
Yes.
Yep.
It depends.
Yeah.
If it's walking, it will.
Most likely.
Yeah, it can. It sure can. It can sink the average that much. It absolutely can.
Yep.
Right? I can have one open valve and be flooding a rack. Now, it's got to be really open, don't get me wrong.
Yeah.
But one TXV, right? Saw this Q bodies. You guys love Q bodies. Technicians and their dang Q bodies.
You don't like Q-bodies?
All right. I had a technician, it wasn't me, it was a vendor that was working in one of my stores. Soldered in a Q body and just forgot to put the cartridge in. I don't know what. Had a rough day. Right? It's probably 2 o'clock in the morning. I don't know. But I got the call about 6 o'clock in the morning. Right? Because that's about how long it took for everything to go to hell. Right? Rack was down. They couldn't get it running. You have one Q body,
Yep.
one TXV. Took out the rack. Could not run.
I mean, that's about that big. So you got a 3/8 or a ½ inch
Yeah.
liquid line just dumping.
Just dumping 3/8 liquid straight into suction.
Yeah, buddy.
Yep, couldn't run one compressor. My liquid's coming in here, right? The 3 things I just told you I've got to have here, right? Actually, I've got to have those 3 things here. Well, what's the practical difference?
A lot. Yep.
Right? That's not my drawing.
That thing is
Right?
pretty.
Isn't it they all look like that. I mean, I'm sure you guys recognize that exactly like that, right? Not every single valve in a supermarket has a strainer, but I would say 90-some% are spec'd to have a strainer, right? So they can help collect crap, dirt,
Those
whatnot.
are $11 a piece.
And don't ever take it off of a Danfoss valve unless you have the crush washer.
That's a true story.
No, you can take them out. You do it all the time.
Change 2 of them. It's cheaper.
And they're only leaking a little bit.
It'll flatten your rack though overnight.
So anyway, my point is, don't take a superheat fail the superheat and then start making decisions until we've checked this.
Yep.
Right? Because I could have all three of those conditions to the inlet of that valve, but I don't to the pin because I've got a restriction in between. My point is, we need to be sure we're checking these if we fail superheat. Okay? That's the point. My liquid's coming through here. It's gonna hit this pin, okay? Now, the pin is gonna fit inside a hole, right? It's just literally a pointy thing with a pointy hole. And they're gonna slide in there, and if it touches, it nearly closes, nearly seals it off. The farther away we get, the more the hole is open, the larger the orifice, right? That's gonna allow more refrigerant to flow through there. Now, what we want to do, we're gonna come out of that as a low pressure liquid with a little bit of flash gas. All right, so let's talk about that flash gas for a minute.
Low pressure, high temperature.
When we go from high pressure to low pressure with a liquid, we're going to boil a little bit of refrigerant because of the change in pressure,
Expansion.
right? That's gonna cause a drop in temperature because now I have liquid and vapor present. Prior I didn't, I only had liquid and it was subcooled. So I could change that pressure or the temperature and the PT chart did not apply, right? Once I pass through that orifice and I flash just a little bit of refrigerant, now I've got a little bit of vapor and I've got a lot of liquid. My PT chart applies, right? So what does that mean? That means the more vapor that I have in that,
The higher it is.
right, my pressure is gonna drop, so is my temperature. Because I've got a pressure drop here for sure. I've got a major pressure drop.
Yep.
Well, the more vapor I have in there, because of the PT chart, the colder that valve body is gonna get. All right, that's why when we walk up to a quote starving valve, it's either got a dirty strainer or I'm running out of refrigerant, it's a ball of ice. Why is the TXV cold when I don't have enough refrigerant? That's why, because my temperature exchange is happening in the valve, right? It's not supposed to. I'm gonna get a little bit, it's always gonna be a little chilly, right? And that's that flash gas. The more flash gas I have, the colder the body of that valve, right? The more I subcool, the less flash gas I'm gonna have. The less energy I'm losing inside the TXV, that's waste, right? It's not exchanging heat with my evaporator, it's happening before that. So I don't want any, right? I can't eliminate it all. But if I subcool, I have very little. So if I've got a nice subcooled 50-degree liquid coming into this TXV, and I touch this TXV with my fingers, it's probably not even sweating, right? It's cool, but it's not cold,
Yeah.
okay? If I don't have a subcooler, my subcooler's turned off, and I walk in and I open this thing up, it may have water pouring off of it. That's a loss of efficiency. That's why. So the colder the body of my valve, the worse it is, the more energy I'm losing in my valve. Does that make sense? That's why an iced up frosty valve is bad news, right? Okay, same applies going out to my distributor tubes, okay? I want my liquid to have that nice liquid pressure drop but still be a liquid as it flows into my evaporator. That's where I want it to start exchanging heat. So if I look at my distributor tubes and they're icy and snow covered, that means I got flash gas, right? That's what that means. Okay, the more, the worse it is. Let's see, what else we want to talk about in here? Oh yeah, so when we talk about TXVs, there's really 4 pressures that we're always going to refer to. Now, the first one is P1. P1 is the pressure that's coming from my thermal bulb, my bulb that's sensing my temperature. It's going to push down, right? And I've always have P1. And I'm always going to have P3. P3 is the spring pressure that I'm dialing in with my tool, right? And then my P2 is going to change a little bit depending on my valve. But my P2 is, I'm sensing this pressure coming out of here, and I'm adding it to the spring pressure, okay? Now, I can do that a couple different ways. I'm either going to do that with an external equalization line or an internal, right? Now, my internal, where I see this P2, there's going to be a hole that's drilled all the way through here. So this outgoing pressure is what it reads, right? That's going to push against the pressure that's coming from this, and it's going to add to my spring pressure, right? Now, a couple things about this. Why? Why would I choose an external equalized valve when now I've got more piping, more copper, more soldering, right? More complex valve, more places for things to go wrong.
Lower temperature.
applications, it allows for more control. Or
It's not the temperature.
the pressure allows for more control. I know some of the control. It's using a suction.
What do you think?
So that if your valve fails and you start feeding liquid through the equalization, depending on where your bulb is, you can still not flood back to the rack. Like,
You're
you
not
can still
flooding, you would
maintain.
flood back to the rack.
No.
You can still maintain.
More
You'd be dumping into the
constant,
suction.
No.
More constant
Interesting.
changes
I like this. This is
in
exciting.
temperature, or in pressure.
So here's my situation. I can have a bunch of different designs on an evaporator. One of the most common that we use is multiple passes. What does that mean? That means I've got a distributor, right? And my distributor feeds separate loops. It's like having 5 or 6 evaporator coils that just happen to sit next to each other and touch, right? But they're really completely separate evaporators, right? Or I may have something far more simple than that, maybe 4 or 3,
Some of those at
Or
that
one.
store is one.
right? My subcooler, got 1 pass, right? How much distributors we got on that? None, 0, okay? That valve is also not externally equalized. We notice, right? On my subcooler, no external equalization. But I go to my walk-in evaporator and I got 20 passes, I've got an external equalizer. What's going on?
There's a
It's a variation.
All right, so here it is. If I'm internally equalized, I'm reading this pressure right here. Okay? Remember that hole is drilled right through there. So I'm reading the pressure right after my pin. Okay? That's the pressure I'm reading. This valve is calculating superheat. Right? It's not cranking out a number, but it's doing it with spring pressure. It's reading the pressure here. And it's reading the temperature here. Is that not exactly what we do as technicians? Yeah,
I mean, it's a little further.
we're reading
down the line,
superheat.
Yeah.
All right, so if this suction pressure here is very different than the suction pressure coming out of my evaporator, because my evaporator has a big pressure drop, my superheat's wrong.
That's what I meant.
I could be off by 7 or 8 PSI. That's how much pressure drop I could have through a big evaporator with a bunch of passes, right? So in that case, when that happens, and I get an evaporator with a lot of pressure drop, I've got to move this pressure that I'm sensing to calculate superheat to the outlet of the evaporator, to the other end. That's when I'm going to use an externally equalized line to offset that correction, to correct that pressure drop.
Not correction,
Right.
not temperature.
It's not temperature. All right, so that means as a technician, when I'm trying to evaluate, I can get an internally equalized valve today, but I got to order this external. Can I use it?
Oh, no, you can use an external in either circumstance, but you can't replace an external with an internal.
All right, so, in a pinch to keep from throwing away food,
Oh, yeah.
maybe, right? But the bigger that pressure drop, the less effective it's going to be,
Yeah.
right?
But you can use an external either or.
Correct.
Yeah.
Right? Because if I'm reading internally here and I move this pipe and it's the same pressure, who cares?
Yeah, it doesn't
It's just
matter.
more piping, right? So can I crimp it off? If I don't need it, let's say I had an internally equalized valve,
No.
and I buy an external,
Cannot.
can I just crimp it off and solder it?
No.
You'll lose your opening force.
I will lose P2 altogether. It won't be here, and it won't be here either.
Yeah, you
As long as I can turn this thing up to 50 pounds instead of 4, maybe.
Good luck.
I just need big ass springs.
Yeah, let's say, just go.
Go to O'Reilly's and
Yeah,
get
it was like go to Advance and buy the spring.
Right. So in reality, what are those pressures? Let's talk about what P1, P2, P3 may be. All right? Well, we know P3 is this spring plus P2.
Yeah.
We know P1 is this force pushing
Plus
down.
P2.
How many pounds is this thing creating? Well, we know that that's referencing P2. P2 is my suction pressure. Right?
Yeah.
So,
And it's calculating
higher than suction.
superheat. So if my suction pressure is 50 pounds, I got 50 pounds on this. That's a lot of pressure. That's what this head is pushing.
It's just in a small
Oh, yeah.
package.
Yeah, it's gonna be above that. All right? It's a lot, okay, is my point. Do I put 50 pounds on here? No, I put 4 pounds or 6 pounds because I can subtract P2. So then I could have a P4, right? P4 is not on my drawing. P4 is this discharge pressure coming into this valve. Now, an interesting phenomena is P1 plus P4 equals P2 plus P3. All right? Now, the reason why that matters, okay? This is why we choose a balanced valve or not. If we choose a valve that doesn't say it's balanced, it's not balanced. Right? What does that mean? That means this P4, as P4 goes up, P2 and 3 also have to increase to stay balanced. Well, what the hell am I talking about? I'm talking about my discharge pressure, my liquid pressure feeding this valve. If I go from 150 psi right here to 250 psi, I increase this P1 plus P2 by 100 psi. I got to increase P3 plus P2 100 psi. Well, my suction pressure is not going to change, and neither is my spring setting.
Your pressure.
My valve is not going to be the same. It's not going to be at the same setting.
Easy.
I just changed my discharge pressure, and I also changed my superheat. You guys got that?
Yep.
The setting on my valve is now wrong. Okay? Just because my discharge changed, just because it's warm outside and it was cold, or vice versa. Right? This is why we choose balanced valves only in supermarkets.
Yeah, that's what I was saying. So
Right?
your bodies really shouldn't.
Yeah, we don't go with anything that's not a balanced valve, right? Okay? I know you're looking at me, those damn Q bodies, you're using balanced Q bodies, right?
Me?
You know, BQEs?
I have them on the truck stock list. I've never bought one.
I have them on the truck.
So here are some Qs, okay? There's a lot of different kinds, but I'm gonna throw these specifically up here because these are the Q bodies that you, like I said, technicians tend to carry because they can change the cartridge and change the size of the valve very easily instead of carrying a bunch of valves. Makes sense. It's a good service valve, right? Let's just be sure we're using the correct one, right? There's lots of Qs, right? The one that we should be using should have a B in it for balanced, right? So any of the BQs will work, okay? The S means it's soldered instead of flared. We should have an SBQ is what we should be carrying, and if we throw an E on there, external equalization, all right? So we probably want the SBQEs, okay? That's the valve we should be using in the supermarket world. Does that make sense?
In any application.
Pretty much.
Yeah.
Yeah, pretty much anything. Let's talk about sizing these TXVs. They all have their capacity stamped right on them, right? Well, except for the Q body.
Yeah.
Cartridge, though, it's got its size stamped on it, right? So if I say I got a half-ton valve, what does that mean? Right? Or I got a 1.5 ton valve. I mean, just 1.5 tons, right? No.
Oh.
No, that's way too easy. That's way too easy. Come on.
Depends on the temperature of the liquid.
You know, say it again louder.
Say it depends on the temperature of the liquid going to it.
In the liquid.
Temperature of the liquid. What else?
Evaporator.
Refrigerant type.
Evaporator
So
temperature.
cooling.
The evaporator temperature.
And your
2.
refrigerant type.
Refrigerant type. 3. One more.
What was the question?
Low temp or medium temp? Oh, I guess that would be your
Temp.
evaporator.
Wait, what
Evaporator.
was the question again?
All right. This 1.5 tons that's stamped right here. What is going to impact that? All right. We just named 3 things.
That would be your,
We're missing 1.
Evaporator
The
temperature.
temperature.
Evaporator temperature.
Liquid temperature.
Liquid temperature.
Refrigerant.
Refrigerant type.
Yep.
Liquid pressure.
And what?
Liquid pressure.
Liquid pressure. Pressure differential.
yeah.
Remember that 100 pounds I was talking about across valve suction to discharge, or 150 or 200, right? Those 4 factors change that rating. Okay? So a 1.5 ton valve may be nowhere near 1.5 tons. I've seen a 1.5 ton valve be worth 4 tons before.
Yeah, which is why sometimes you'll see like, okay,
That's an extreme example, but it does happen when we start plugging in the math. So let's talk about how we're going to plug in the math, right? Because we can easily screw this up,
okay.
right? Going off that 1.5 ton and throwing it in might work if everything else counters and offsets itself, which sometimes happens, sometimes does not. All right. So the first thing we were talking about is refrigerant type up here at the very top. You can see I've got refrigerant type. This whole chart is just broken into 2 types of refrigerant. That means I got pages and pages of these charts for different refrigerants, right? Yeah, and different body valves. Yeah, this is a huge file. Okay, so the first thing I'm going to do is find my gas type. Okay, it's also going to throw out the acceptable heads to put on that particular valve for my evaporator temperatures. That was the second thing that Ian said. Okay, and if we look at, and we're going to stick on this 1.5 tonner here, just because it's even numbers, right? If we look at this guy at 40 degree evaporator, medium temp, it's worth 1.5 tons, you know, 1.53 tons, right? But if I run this guy at minus 40, it's a 1 ton valve. It's lost efficiency as that pressure is dropping, as my temperature's dropping.
That's actually not that much for.
Right, it's a half ton,
80 degrees.
30%, it lost 33%,
Over 80 degrees, yeah.
right? Something like that. All right, but it's got a sure enough effect, okay? So we don't want to discount that.
Yep.
All right, the next piece, so we've got our gas type, now our evaporator type, we've covered that. All right. Correction factor, liquid temp. Okay, and I told you I blew it up so we'd be able to look at it. This is the same correction factors that we're going to use for everything. All right, now I blew this particular example up so you can get an idea of what this looks like. Once again, if we look at 100 degree liquid temperature, you can see my correction factor is 1. Everything is designed for 100 degree liquid. Okay, but I'm running low temp here. I got a 1.5 correction factor for 50 degree liquid. Right, so my 1.5 ton valve, what is that, 2 1/4, something like that? About 2 1/4, you know, 2.25 tons is what I just went to. Okay, all right. My pressure drop across the TXV. This is the difference between, now here's, this can get complex, and the reason this gets complex is because we hardly ever have a liquid port right at our TXV. We can't actually measure the liquid pressure going into our TXV. That's disappointing. It would make things a lot easier, right? But when we're looking for that pressure drop, usually we gotta go like all the way out to the rack. We gotta read that near our solenoid. That's where our last service fitting is on the liquid side. All right? Because of that, we've got to calculate the liquid drop, pressure drop, from that fitting all the way to the TXV. We got. Remember we looked at that chart for our solenoid? It can be up to 5 pound drop if it's sized correctly. We got to calculate that.
Add a Pearson valve.
It was working.
Do what?
Add a Pearson valve.
No.
And leave it.
All right, but we got to calculate that. We got to calculate the drop all the way to my case. All right, and then I'm going to take that away, and my distributor. My distributor is also a drop, and we'll talk about that in a minute. We haven't even got to that yet, right? But I'm going to have a drop through the distributor, right? I'm going to have a drop through my cap tubes. I'm going to have a drop through the evaporator, okay? And I got to come up with that actual drop through that whole system, and that's going to be my correction factor here. That's what, right? We can see 100 psi is 1, all right? Now you can see why I go with 90, right? I like 90 because that gives me 10. I can lose 10 pounds on the way there, right? Does that make sense? So once again, if I've got a 100-pound drop there, if I've got 100 pounds from the inlet to the outlet of my TXV, then my 1.5 ton valve that I'm feeding with 50 degree liquid that's now 2.25 is still 2.25 and I'm all set, right? As long as I've got 100 pounds. But if I don't have that liquid pressure regulator and it's summer and I've got 250 psi discharge, then that factor, my valve starts getting more efficient. Check that out. Let's say I go up to 200, 225, because this is low temp. So my point here is now I've got a correction factor because it's summer of another 1.5, right? And I was already at 2 1/4. What's that gonna take me to? About 4 tons? My 1.5 ton valve is worth 4 tons.
Well, that's for.
I can easily miscalculate that. Yes, sir. You can put your hand down.
Right, so, is that the difference between a, like an VZP and a VZ power head? Is that P for pressure?
I got a whole
limiting?
segment on power heads, but I will answer your question.
Cause you said if the pressure drop changes across your TEV,
Right?
if that's a pressure limiting power head, is that what it's doing?
No,
Not limiting that
That's
pressure?
keeping your saturation as.
Okay.
nope.
Okay,
Right.
we're good.
So his question was about heads, power heads, thermal heads that have a pressure limiting capability.
Yeah.
Right? They're gonna have a P on them, right? And he was wondering if that relates to this, okay? And it doesn't.
Okay.
Because eventually I'm gonna end up here anyway. That P is gonna slow down my pressure is gonna increase on a nice scale like all my other valves, and it's gonna kinda hit a wall when it starts to climb. It's gonna go flatten right out, right? Really, that is just to keep from overloading a single compressor that's trying to start up and keep it from getting just nailed with too much suction pressure. So it's gonna hold that suction down, right? So my compressor can get running and get control of the load until the superheat on the case falls and matches that pressure, right? And then it turns into a regular valve, okay? So that's all that is for. We won't see that on a rack, shouldn't, because we got a rack.
Some walking about it.
Yeah,
So it'd have to be a big one, right?
Yeah.
They're worried about,
Ryan's
they're worried about one evaporator hurting an entire rack, suction pressure wise. That's gotta be substantially bigger. One other piece I forgot to cover here, I'll back up a little bit. On my external equalization line and my bulb placement, this is a little bit controversial,
Bulb
Doesn't matter.
before the equalizer.
okay?
Doesn't matter.
Who's the trending?
Do we all wanna vote?
Yes.
Anybody who thinks it should go before the equalizer line, raise
Should
your
it
hand.
or does it? Doesn't
Anybody who wants to see it after the equalization line, raise your hand. All right, okay.
matter. Right.
So in practice, it really doesn't matter, right? If I've got a problem, I got a problem. Then I gotta fix it. Doesn't really matter. But here's the engineering, all right? Here's what your engineer's gonna say. This is why it's gonna be set up the way that it's set up. I hear you. It doesn't even matter,
They
right?
say a lot of things.
They say a lot of things. Okay, so my liquid refrigerant is flowing into my evaporator and it's coming out here, okay? This is why I wanna sense this pressure here, because I got a bunch of distributor, right? I got a bunch of tubes. So, let's say I'm coming out at, just for easy numbers, 50 pounds, okay? Coming out of this at 50 pounds, and I'm coming out of here at 40 pounds, okay? 10-pound drop. That's more than I'd actually have, but just keeping it all straight, okay? So this is gonna detect that 40 instead of the 50,
Yes.
right? That's gonna be my P2 that combines with this. This is gonna have the same refrigerant or similar refrigerant in it that's in this whole system. So when it detects that temperature, PT chart's gonna apply. It's gonna have some liquid and vapor inside this bulb. PT chart will apply. So that temperature will equal the pressure of its saturation. That's gonna create a 50-pound pressure pushing down,
Yep.
right? All making sense? I dial in the difference on my spring and I'm good to go. There's my superheat. All right, so if I look at this, the way my P2 is coming in here, it's just open and it presses against the top of this thermal manifold. My liquid pressure is flowing through this orifice. The only thing keeping this liquid from traveling up here and going out P2 is the seal around this pin in the body of this valve. That pin and that body move. There is no seal. It's oil, right? Remember we talked about refrigerant oils, got to travel through the system? I got to have a little drop of oil in there to seal that, right? If I lose that oil, or that pin wears out, or cuts a groove into that brass body, either one, I'm going to start passing liquid refrigerant into here, and then out my expansion, my equalization line. That's what'll happen, okay? So, when I've got liquid coming out of my expansion line, it's going into my suction, and it is changing the superheat right here.
Yep.
If I put my bulb upstream of that line, it will detect the real superheat of my evaporator.
Yep.
So my engineer is going to tell me to put it right here. All right, so what would be the downside of me mounting it here?
If you bypass through the equalization.
It's going
line,
to
it'll
read a
affect
higher,
your
or it's gonna read
Wait,
lower.
one at a time. Ryan, go ahead.
So if you put it there and you're bypassing through your equalization line, you'll read a cooling temperature.
So that's gonna close it down.
Right, it's gonna cause the valve to
Yeah.
close.
And you'll.
I'm technically starving my evaporator now,
Yeah.
right?
But,
Correct.
hear me out, that's why we don't insulate them because of the location, or the application, because it's underneath, in the little box, everything's
Well,
relatively,
your return and supplier is basically the same, so.
depending on that's why the application is for.
You're returning your supply.
What I'm saying is like in air conditioning, you insulate the bulb because there's such a big temperature.
Okay, right, we'll get into that in a second
But
too.
I'm saying,
Let's wrap up this external
That's what I'm saying,
valve. and
application of it.
And then we'll talk about the bulb location. All right, well, I'm just talking about in regards to this line, anybody got anything to say about putting it here?
No.
Go in.
Yes, sir.
If your bulb is upstream of your equalizer and you're putting liquid through your equalizer, you're flooding back to your rack and you're not sensing that superheat, so that valve is not
Bingo.
going to close
Oh,
down. You're
wait.
sensing artificial superheat,
See,
Okay.
that's my boyfriend.
whereas if you
All
go
right.
after the equalization line and you lose that.
Let's think about what he just said. All right, is that right?
Yeah.
So what he's saying is if I'm flooding through this equalization line and I put my bulb here, then I'm accurately controlling my evaporator,
With no failsafe.
right? But I am flooding my rack with the liquid that's coming through this line and going to my compressors. If I move my bulb to here, I'm no longer controlling this evaporator correctly, but I am protecting my compressors.
Yep.
There is no
So
range.
you'll
Is that right?
It also depends on how far away, like in practicality, like that bulb
Right
and
here,
that equalization line
a
are so
flooding
close
equalizer
together.
line with it mounted below, or before the equalizer,
Yeah, and if you notice, the frost is making its way back.
all the way to the rack.
Yeah, sure.
And back to your.
Mount it right next to the
Okay, all
equalizer.
right, so that's why this is controversial, guys.
It's
Both,
not gonna just go one way though.
both ideas are correct, right? Damn it, right? Both things are right. This is one of those things, you gotta choose, do I wanna protect the rack?
Yes.
Or do I wanna make the best temperature I can on this case? And if I have a problem with the rack, find it.
Trying to make that
Right.
store score every.
Well, that's what our engineers are telling us to do in most cases, they're gonna choose the rack, right? Because it gives them the best control, the case.
If you
It
take
gives them the best control of that case. Because they don't maintain the rack, right? But as a rack mechanic, I wanna protect the rack and I'll know which case is the problem because it's the one runner warm, because it's got 40 degrees superheat.
But we make more money on a compressor change out there.
All right, my point is, this is controversial. I don't care which of those decisions you make on which way to go,
Make sure
It's not-
right? But I want you to be educated on why and be able to defend your answer. You understand what I'm saying? You're gonna find both of these from the manufacturer,
The case.
right? The overwhelming majority are gonna put it, quote, upstream, right? Because that's what the engineers are telling us to do in case that leaks, all right? But you're gonna also find field guys have moved that bulb downstream, right? If my case is not making temp, that may be why. That could be part of the problem. How would I know that? Same way, I should be checking it anyway. My external equalization line should have no refrigerant flowing through it, none,
Not like that.
right? It's supposed to detect pressure. It's supposed to take that suction pressure and push it against this bulb. If there's liquid refrigerant flowing through it, it is leaking,
Yes.
right? My valve is not working properly.
Yep.
It needs to be replaced. It is worn out. Guess what the next section is?
What is it?
Sensing bulbs.
What's that?
All right, this is a pretty cool chart. Now,
I like charts.
when we look at a sensing bulb, there's a couple things going on in the sensing bulb. Right? I told you there's a refrigerant or a similar refrigerant in the sensing bulb. Okay? Well, which is it? Is it the refrigerant or is it a similar refrigerant? We actually can know that. It's on this chart. It'll tell you whether it's a blend of refrigerants or if it's one refrigerant. Okay? So if anybody ever gone into the parts store and tried to buy a 449A valve, right? They're not gonna have it, right? They're gonna give you a valve that works. This works, but it doesn't have 449A in it, right? It's got a refrigerant that's gonna behave very similar, or it's gonna have a blend that's gonna give us a similar effect, okay? So that's the first thing to note, is that they used to manufacture valves, heads, that had the exact refrigerant we were using,
Right.
back when we only used 3 refrigerants.
Right.
It was either pink, green, or white.
Yep.
That was
Now they're all gray.
pretty simple, right? All right, today that has gotten really complex, and we've got midpoint, we've got all this other stuff going on, right? Well, that's gonna happen with the blends they're throwing in here. So it's no longer, we're no longer gonna find an exact refrigerant, okay? Well, that's gonna cause, what that's gonna create is I'm gonna have a slightly different superheat setting at different temperatures, because it's not gonna press perfectly as my superheat changes.
Yep.
They're gonna get off a little bit, all right?
And that's why you'll see it swing.
So Sporland was kind enough to give us a chart about how much off they're gonna be. That's what this chart is. This chart is gonna show me how much my superheat will vary
Look at that.
based on the temperature of the evaporator that it's running. Kinda cool. All right. Well, if we look at this, here's my evaporator temp. This is in Fahrenheit, okay? Now, my evaporator temp, remember, TD about 10 degrees, right? So this is gonna be about 10 degrees colder than I'm running. So if I'm running a -10 box, -20 is gonna be about as cold as I go, okay? On the other side, my 20, give me a 30-degree, yeah. So this is kind of my range in a supermarket, right? I'm gonna run between these two numbers. So what I would really like to see is a head that runs flat across those two temps, right? Well, if I look at that, we'll look at this C charge.
It's very significant.
It's sitting at -20, it's at 11 degrees of superheat. It drops down to 9 and goes back to 11. That's a pretty minor change. So that's one of the reasons why we see C charges a lot. All right? This is how a bunker works, a dual temp. Okay, this is why it still works. If I set my superheat at 12 degrees and I do that medium temp, guess what?
Yep.
Pretty dang close at -20.
So you don't
How
have to
about
set
that?
them in low temp.
Maybe 1 degree of superheat different. Pretty minor. Do what's that?
So you don't have to set them in low temp.
That's what you just learned, right?
Yeah.
Depending on your head. Now, if I'm running a Z head, yeah, I got a problem. I got a problem.
Would it be a CZ? Simple, it's, oh, I guess, never mind.
No,
Never mind.
he's talking about these.
Never mind, never mind.
All right. Okay, but that's why in the supermarket world, there's a couple, we're gonna see VGAs and we're gonna see Cs. They're gonna be our most common heads because they span that temperature range with very minor differences. All right, so the other challenge I hear is I hear techs say, well, I set the superheat, but the case hadn't pulled down, so I need to go back tomorrow and dial it in. Yeah, probably not. If I'm close, now if I've got a 90-degree frozen food door, right? My chart goes off on 90 here. I don't know where that C charge is going, but I can predict it's going to be up here. It's going to be very different.
Yeah.
Right? But if I'm pretty close in that 30-degree range, right? Probably going to be pretty damn close, all the way to -20. Okay, it's all going to be really close. All right? Does that make sense?
It's good to know.
Ding.
So technically speaking, I should just throw away all my VZs and just VCs and SCs and all that.
So I would always go back with the valve that's there. There's a reason.
Well, I'm saying specifically just.
The reason they've chosen it. But I would also recognize when I look at it, that it's gonna fall into this category or this category.
Or can I just drill a hole, put an access tap,
And change the refrigerator?
and just put the right refrigerator?
Sure. Knock it out, man. So a couple designations when you see this type thing or you see printed documents about my valves, these heads. A couple things that are gonna stand out, I'll tell you what they mean, just so you know. You're gonna hear things like cross-charged, all right? If this says that it's cross-charged, liquid cross-charged, C-body as a cross-charged valve, what does that mean? They're using more than one refrigerant in that head,
Okay.
all right? They've made a blend, okay? That's all that cross-charged means, all right? Liquid, what does that mean? That means most of the valve, most of that head is full of liquid refrigerant. There is vapor, so my PT chart applies, but it's a very small amount of vapor, all right, versus gas. The VG is mostly vapor with just a drop of liquid in there,
It's very gas.
all right? Okay? And you notice the VG is not cross-charged,
Sorry, no.
okay? It's not cross-charged, it's one refrigerant type, specific refrigerant type, okay? So anyway, that's what that stuff means. We don't really, that's not our place to engineer which one's supposed to be on there, but that's what those values are when you see that. All right,
I was saying
So SC is the same thing as like SC,
Yeah,
sir,
where you go to say like SC,
SC?
so same like.
like for 404A.
Yeah.
Yeah,
Yeah, I always think like C is cool, and then Z is 0, so like low.
What's what
I
it
mean, that's
used
not
to
a bad way to look at it.
No, it used to say C was like, -10 to 30,
No.
and then the Z was
No.
-20.
No.
We always do
Zero.
C's, medium temp.
50,
So-
50 to -10.
so there is a distance that those temperatures
50 to -10.
range for each head. But be careful there, based on that refrigerant type, because they're blended or using something different, that'll change. For instance, the C charge, the book says that it's good to -10, right? Look at the asterisk. For 448, 449, 407, and 404, -30. Okay?
Yeah, I was on 50 to, plus 50 to -10.
Right, so anyway, just, there's a whole chart of it. The one thing that I thought that I had in here was a picture of the bulb. So we'll talk about the bulb before we go into that. I said I would. A couple things about it. All right, bulb location. So on my pipe, when we say 12 o'clock, we're talking about right there. Okay, 3 o'clock, 6 o'clock, 9 o'clock, right? Where do I put my bulb? You can find just about any argument to support any idea you have, depending on where you go, all right? Air conditioning, those guys, yeah, they sometimes go to 12 o'clock, they do.
Tail up, 12 o'clock.
You won't find any refrigeration manufacturer telling you 12 o'clock is good for anything, right?
That's 'cause of the
They're always gonna tell you 3 o'clock, 9 o'clock, 4 o'clock, 5 o'clock, right?
Not
They're-
12 or 6.
Right.
There's only 11 and 2.
Not at the very bottom, not at the very top. They're gonna be out on the edges and usually just a little below the edges, okay? That's kind of, 8 o'clock. That's kind of the general consensus, all right? But you can find conflicting arguments if you would like to, all right? Now, the concept here is, we shouldn't be flooding.
Does not
At all.
matter.
It should be the same temperature.
Oil.
What difference does it make?
It don't.
Shouldn't make any difference if we're not pooling liquid or oil. So that's why I would definitely stay off the bottom of the pipe, right? Because if I've got oil, it could
Well, I
interfere
mean,
with that. Yes, sir.
most of the time,
He was lagging.
we don't insulate our bulbs.
That's the next thing I want to talk about. Right.
So, I feel like it doesn't necessarily have to be insulated so much as just sealed.
Okay.
I have a comment on that.
Yeah?
I do have a comment on that.
Go ahead.
It should
I
be
don't feel
anything.
like the bulb should have to be insulated because it's in a portion of the case that has very little airflow. So it should only be affected by the temperature of the pipe and not it's not in a direct airstream, so you wouldn't necessarily get air temperature flowing across.
Then that's what,
Well, I mean,
Okay.
neither is an air conditioning one, it's the temperature difference, not the.
Anyone have a counter
You're still
idea?
pulling air through the coil.
Yes,
some manufacturers, Phoenix, puts it right in the return airstream,
Uh-huh. They do.
sticks it right there, but they seal it to the suction line.
Okay.
With
in applications where there is a temperature difference, a large, depending on what you consider large, temperature difference between where the location of the sensing bulb and the coil temperature will determine whether or not it needs to be insulated. So for example, in a refrigeration case, the temperature that the supply air and the return air is, like in a glassware case, for example, is not very different. It's not like you're getting 75 degrees and like an air conditioner and 55 supply with a 40-degree coil. You are relatively close. I mean, you can put a line on your suction clamp, and typically if your superheat set in your case is stable and you have like a -2 discharge air temperature, a lot of times your suction line temperature will be damn near.
I have seen
All right.
that.
so let's talk about that phenomenon he just said. That's kind of key.
Yeah.
All right, so in supermarkets, we agree, we don't see insulated TXVs. The bulbs are not insulated, okay? So if I have 10 degrees of superheat, right, that's kind of a standard for medium temp,
Yes.
right? 10 to 8, 10 degrees of superheat. And that's 10 degrees above my boiling point of my refrigerator, right? That's what superheat is. 10 degrees above the boiling point of that refrigerator. And I've got a 10-degree TD on my coil. That means that leaving air of the coil is 10 degrees higher than the boiling point. I have 10 degrees and 10 degrees. My supply air and my superheat are gonna be exactly the same temperature.
Yep.
So what am I insulating from?
Return air.
Okay, right?
Nothing.
Okay, if my bulb is in my supply air, they're exactly the same. If my air, I'm in return air. Now I've got the TD we were talking about earlier. This is the one air conditioning guys use, right? Supply to return, return to supply, whatever you want to call it.
I was trying to.
Oh, that's a different number, isn't it?
Yeah.
Yeah, right. So if my bulb is exposed to that, maybe I got 20 degrees. It's not uncommon. Instead of 10. What if my superheat that I'm setting on my case is not 10? What if it's 4?
Yep.
Right, that happens.
Yes.
We get cases like that. Now I've got a 24 or 16 degree difference. Should I be insulating? Yeah. Yeah, I should. Right? Should I be sanding that copper pipe before I add my bulb? Of course.
100%.
Should I be adding thermal mastic before I stick the bulb?
No.
No.
What?
You don't want anything but copper to copper.
No, cork tape.
And then should I be cork taping the crap out of everything?
Only if you want to be shot by your
All
fellow
right,
employees.
so the answer to these questions are, of course, you guys know this is best practices, right? We know that from air conditioning, except for
What
you
is
guys who
this,
have
what
air
is this
conditioning.
thermal stuff you're talking about?
You
I don't
losers.
do one.
But everybody else who's been, no, just kidding. Just kidding. All right, so yeah, it would be a best practice to insulate all this. It'd be best practice to use thermal mastic. It'd be best practices to sand the crap out of it. It'd be best practices to put 4 pipe clamps on the dang thing and screw them down as hard as you possibly can. And then wrap it in cork. And then wrap that in foamy. And then, yeah, all right, all that would be best practice. The question is, does it matter?
No,
No.
absolutely freaking.
All right, so going back to our distributors, we were
Not
talking
enough.
about not insulating, right?
Doesn't matter.
Right? It is such a minor difference that the cost of a piece of foam Robotex
Yeah.
doesn't pay for itself.
Walmart ain't buying that off.
So it's very minor, right? It's extremely minor.
$5,000.
That's why it is a best practice, but we don't actually do it.
So your Y10 valve and your discharge line temp?
Well, that's
is that gonna be
different
insulated?
because you're in a rack house.
Yeah, that's different.
Yeah, I mean, technically not, but if you think about that, we're reading 210, 220 versus, that's a 100-degree difference.
Yeah.
Right?
Yeah.
That's not 16 degrees on the extreme.
That's why.
Right.
If we heated up the rack house, we got a bunch of heat.
Right. Just take her up to 200 or so.
But it's
Right about
not,
where water boils.
Yeah.
And yeah, it'll be good.
I'm just cutting.
Y10 will read just fine without insulation. Absolutely. All right. Okay, so now we nailed down location. Now, seriously, we're not gonna go through the trouble of insulating something unless we're having some real issues and we're trying to get everything just really, really perfect,
Last case.
right? But we do need to read that temperature. So that means that copper does need to be clean. If it is green, you better sand it, all right? That means that I'm not putting this bulb on a fitting, right? It's going on the copper pipe itself,
A nice
right?
straight.
I'm going to clamp the living out of it
do not put an impact on it.
Without crushing it.
Yeah. Take your little
without
hammer, make your
damaging
flat
anything,
spot.
right?
Make
But
your
it's
flat
gonna be
spot.
secured. I'm not using zip ties.
I like those.
I'm not
stainless
zip
steel.
tying my bulb. I cannot, we're not using zip ties.
We are what?
Any other questions about a mechanical thermal expansion valve? Yes, sir.
On a hot pull down, with that swing,
Yep.
about when would you expect it to stop having a 4-degree swing like that? Like when it
That
gets.
chart shows you.
Yeah, that's
It's
all on the chart there.
at all times you're in that range.
Yep.
Okay.
Yeah, all the way out here to
So
six.
That's
Maybe
what I was
cross.
saying is that it's
Right.
not, it's,
You are always going to have some swing.
yes.
All right, so let's talk about setting this valve in the swing, okay? Yeah, I needed to cover that before we went on distributors. So when I'm dialing in the superheat, when I say, how many degrees of superheat do you have on your valve? All right, or you're telling me, I got 10 degrees of superheat on my valve. What does that mean?
Means
Okay, so we know how to calculate superheat, right?
Plus minus 5?
The challenge I've got in refrigeration is when I set up to take those two readings, my suction pressure and my temperature of that line, right? My suction pressure should stay stable. If it's not, if it's moving, my superheat means nothing, right? Because the temperature is gonna lag behind the pressure change. So I have to have a stable suction. That's the first thing. If my rack is hunting and it's going all over the place, I got cases slamming on and off, all this other stuff, I gotta turn off enough stuff, turn on enough stuff to get a stable suction. I must have a stable suction, that's number one, right? And it's gotta run that way for a bit, 15 minutes, 20 minutes to change the temperature of that pipe to match, okay? All right, if I'm changing my suction, I'm changing my boiling point, I'm changing the temperature of the copper for the same superheat. All right, so that's number one. All right, the second thing is I'm gonna take that temperature reading. Now, on a mechanical valve, I'm gonna see that temperature change. It's gonna be all over the place, all right? My suction pressure, as long as I ensure it's stable, then the change in temperature that I'm reading is my superheat. It is a change in superheat. If my suction pressure is moving also, all bets are off, all right? Okay, so when I say 10 degrees of superheat, and I've got a temperature that's moving, where's 10 degrees?
In the middle.
10
Right.
degrees is nowhere.
So a common thing is in the middle. Anybody got an alternative idea to that?
the low
at the bottom of your
before the superheat.
He says bottom of the swing. Okay?
Whatever,
I also don't go to 10, but.
well, I mean, that's why your case has to be a temp.
Low temp.
Or plus or minus 10,
Close.
10 to 10, but it's.
So I got bad news for you, my friend. The closer to temp I get, the more I'm gonna have a swing.
Yes.
Damn it. What? All right,
Yes.
let's back up. Okay.
Let the grown-ups talk.
Let's back up. So a 15 to 20 degree swing is actually fairly normal on low temp ice cream cases that are at temp.
Yes. We're done.
No kidding.
Yes.
Right? So now that's an extreme version. I just laid out probably the worst you'll ever see. It almost looks like hunting, right? It's not quite that extreme, but it is pretty significant. Okay? Why is that? Well, we just went through all these factors on sizing our valve. Okay? They're not going to size that valve at minus 10 degrees because it will never achieve minus 10 degrees. People are shopping that. They're opening the doors. Right? So they're going to oversize that valve to take that heat when the doors are opening and they're getting hit with load. They want that valve to be able to pull it down there, which means if it's down there and the doors are closed and it's happy, that valve is all cool, it's oversized. Well, what's a sign of an oversizing valve?
Flooding.
Hunting.
Hunting.
So it's going to start hunting. It's going to start hunting properly when everything is right. We're going to see that valve hunting, okay? Now, once again, I gave you the worst case example because it's the worst here. That's where not understanding how to figure out my 10 degrees, what's 10 degrees, comes into the biggest play.
All the
All right? So we got to know what the manufacturers are expecting when they tell us 10 degrees of superheat. What do they mean? That's what matters. All right? What the manufacturer says they mean when they give us the spec, 10 degrees. When they give us that spec, how are they figuring it out? I can argue which is right. Both of you are right. Okay? The question is, what is the manufacturer asking for when he gives me that spec? All right? Now, in refrigeration, this is different than air conditioning. In refrigeration, it's the bottom of the swing. All right? Hill Phoenix, Tyler, Zero Zone, sorry. All right? All those guys are talking about the bottom of the swing. My air conditioning guys, they're talking about the midpoint. Okay? All right. So when I say the bottom of the swing, what do I mean? Okay? I'm saying if I strap my temperature probe to my suction line and I see that temperature drop and my superheat drop down, The way this plays out, this could be a 15-minute cycle. This may be even 20 minutes. It takes a long time to see this full cycle. But what's going to happen is my superheat's going to sit very high. It's going to kind of chill out there for a little while, and then I'm going to see it start dropping. Right? It's going to drop down, and it's going to hit a bottom for just a second, and it's going to start coming back up. And it's going to go back up, and it's going to sit up there at the height again for a long time. Right? When I say the bottom of the swing, I'm talking about that coldest temperature achieved that it only achieved for a split second and then turned around. That is the bottom of the swing. That's what my equipment manufacturer is speccing when they say 10 degrees of superheat to that point.
So if you look at their chart though, right there, it's showing you what your swings are gonna be, right?
No.
No.
Nope.
That's your power head, like, temperature range.
Yeah.
You're looking at this superheat range,
Yes.
right? That's telling me my usable superheat range, where I don't want to spec a valve outside of this range.
Call the manufacturer.
Yeah, because
I don't want to spec a temperature and a pressure that is outside of that range.
Okay.
In the right superheat range, but you're still gonna have a swing.
That's why
as it
your
feeds.
10-minute theory about only waiting 10 minutes instead of like 15 or 20.
All my
is-
superheats, if you look at all my graphs, I'm doing something right because they
You
are
are,
always
you
pins
are,
are big.
because you're
You can't
taking-
even see the set point line in a lot
All
of
right,
times.
so why do we swing, okay? I kind of gave you a hint, but the reality is the closer that valve is sized to its current load, right? If they align and they match perfectly, we have zero swing.
So general rule of thumb, like on a medium temp, for whatever, medium temp.
Mhm.
Generally, when the case is a set point, under good, like, if, let's say open case medium temp, okay?
Cheese wall.
Yeah,
Yeah, so open case, medium case, airflow's good, loads suction stable. The set point's 33. Roughly, what should your swing, you?
yeah, it's gonna be very minor on
Very
that
minor.
case setup that you just described. It's gonna be very minor.
About 5 degrees.
And I gave you the most extreme example.
No, it should
The
be
most
much
extreme
higher.
example is ice cream. That's the coldest thing we got in the store.
Yeah,
Right?
well, yeah.
And it's gonna be designed to handle the heavy heat load that it's gonna experience after defrost when it's being shopped.
Yeah, I feel
Right?
like 5
So that valve at minus 10 is gonna be oversized.
Yes.
When the case is at minus 10.
Yes.
Right? That's the worst, most extreme. The most mild version of this would be our meat prep. Medium temp, right? It's very close to ambient temperature already. It's sitting at 45. It's changed from defrost to back to temp. It's about 5 degrees. Barely see it on a TA,
Yeah.
right? There's a little
Yeah.
hump,
Yep.
tiny little hump, right? That thing is going to have next to no swing. It's going to be 1 or 2 pounds.
Now-
It's going to be very mild.
Would that be because the valve's not feeding?
Because it's the correct size.
Yeah.
It's and it doesn't need to be oversized to recover from anything, right?
The load doesn't change that much.
That load
Yeah.
doesn't change. It's
Yeah,
the
so-
same load
Yeah, so
constantly.
our
Yes, sir.
pressure's gonna
So the
drop.
colder we go, the more likely the valve is gonna be oversized, and the more likely we're gonna see a bigger swing?
Exactly.
Yeah,
Yeah.
okay,
Right.
and that was.
Now, if I miss the engineering and I oversize a valve, that's what it's going to look like too, right? And I can do that when I'm changing a walk-in box that's not making temp, and we're reinventing the wheel. If I carried a 1 and I should have subtracted it,
Yeah.
and I end up with the wrong size valve, I'm going to have a huge swing. That's what's going to tell me that I'm oversized, right? What's going to tell me I'm undersized? No swing at all. That's going to tell me my evaporator is bringing more heat to my system than my TXV can handle. It'll be coupled with high superheat, right? So if we think about that, when we've got a system that's not working, something's wrong, and we've got high superheat, we're trying to dial it in. When we have 30 degrees of superheat, we got no swing. It's sitting there at 30 degrees,
Yeah.
right? Yeah, that's because something's wrong. Probably my liquids. Now we know, right? Subcooling.
Yeah, we're
Right,
subcooling.
right.
We're
Got 100 degree. Yeah, right.
Or
Right.
open it.
Something like that, okay? So as my valve becomes undersized, I have no swing. When it's sized perfectly, I have no swing. When the valve is oversized, I start to have a swing. By design, my low temp stuff is gonna be oversized so it can recover and pull down. So the lower the temp, probably the higher the swing.
Yeah, and that makes sense.
I'll see that on a walk-in box, for sure, because it's used to heavy load changes, right? It's, yeah, that valve's oversized, for sure.
Or
Distributors.
when you look at it, go,
So I need a distributor if I have multiple passes in my evaporator. We talked about that. My subcooler has one pass, no distributor, right? But most of my evaporators actually are multiple evaporators, all bolted together, all soldered together, right? Each one of them has its own circuit. Well, that means my TXV has got to evenly distribute its refrigerant to each one of those evaporators, thus the distributor. That's the whole point. Now, on a technical side, or on a technician side, there's not a ton that we got to do to this, right? As long as it's clean, right? My strainer tends to take care of that. On the startup side, I could have the wrong one. Easily, right? Happens. So you can see I've got a drawing here that shows this piece right here. This is my changeable piece. This is my maintenance item. Okay? The only other thing that I can do as maintenance is if I have a stopped up tube. I've got one that stops feeding, right? I'll have one that's a different temperature. They should all be exactly the same temp. Whether that's too cold, like we were talking about, whether that's growing ice, right? They should all be the same, is the point, if my distributor is working. If I've got one that is not, I got one that's warm, and everything else is cool. Okay, it's stopped up. It's got some crap in it. Mineral oil, it's wax, for sure. Add hot water, that's gone, right? It could be oil with POE. Hot water, once again, solves that problem, okay? Now, if I do that, if I add hot water and I clear my problem, my case works, am I good?
No, you have to dry it off.
I gotta go, because you have ice and it's gonna bother Corey. Everyone except Corey. Our next step is gonna be dryers, right? We got a dirty system. We're gonna be changing our filters in our liquid line, okay? Because we gotta clean that up. All right, it's gonna happen again. We're gonna have it in different places. It's gonna move throughout the store, right?
Big question. So let's just, new cases come in. This kind of more at startup, guys. The cases have the little mini dryers inside of them. You recommend taking them out? Because that's an extra pressure drop.
Right.
Before the vacuum and everything.
Yeah.
You know?
So we got little, they look like air conditioning dryers, but even smaller, right? In the liquid lines, right before my TXV. Do we need them?
No.
I was thinking,
No.
So I will say this, if my system is clean, then they have no purpose,
take dryers out.
period. If my system is dry, and I have no acid, I've got no copper shavings floating around, I got no contaminants in my system at all, then they have no purpose. Do I have that system?
No.
Show it to me, I'd like to see it.
Yeah. and you
Well,
got
when it rolls off the
big old
factory
dryer,
line, you know.
It's full of crap. No, we've cut it, the stuff we find in liquid line, oh my God, headers, anyway.
Alright.
Yeah, no, we got crap, we got trash, right?
Yeah.
I love Kalos, it's an awesome company. Do we ever strike a torch and put it on copper with out nitrogen flowing? It might happen, maybe,
We have a
right?
whole class that.
Might happen, all right? Have we ever not pulled a vacuum, right? Have we ever accidentally not purged our hose while we were trying to connect something
Never.
and push some air into the system? Does that ever happen? Right? Anytime any of that happens at all, I need a dryer to fix it. Okay? If I put one in the case before my TXV, will that help?
No.
Right up until it's full.
Yeah.
Once it's full, it's not going to remove any more moisture. It's desiccant, right? It's just like a desiccant wheel and my dehumid, except I got no way to reactivate it. That means once it's full, it's done.
Hot water though,
All right, so then if I am reactivating it in place, all I'm doing is putting the water back into the refrigerant, right? I'm rejecting the moisture I collected. It's coming back, right? It's coming back. So my point is, all right, they serve a purpose when the case is new and they're fresh, right? If I've got one that's 20 years old, is it gonna collect more water? Probably not. Right? If I've changed my liquid line dryers on my rack because they were stopped up, what do you suppose is going on in those? Same refrigerant.
Yep.
They're done, man. They need to come out. Okay, so here's my orifice. Right? This is the piece I can change. Right? And this is Sporlan. There are others. Danfoss is coming up, pretty fast and furious
I don't
with
know
this.
why. I have
Alright.
appreciation.
But on the Sporland side of things, there's a couple things about my orifice, all right? One, the letter, okay? The letter is the model, is gonna be about what it fits physically, okay? It's gotta go into, there's a bunch of different distributor models, okay? My model, my number, my G has gotta match that body, right? So it's gotta, in order for it to fit. The orifice number is gonna relate to my capacity, all right? How many tons I can move through this thing. All right, my number over here on this chart, I look at my refrigerant, I look at my evaporator temperature, and it's gonna give me a tonnage. All right, that's what this is gonna be here. What do you suppose we gotta compensate for? Anybody wanna guess?
Oh,
Pressure
Liquid
drop,
temperature.
liquid temp.
All right, liquid temperature. Yeah, if I'm subcooling this, do I have a correction factor?
Yes, you do.
Yes, I do. Is it the same correction factor? Yes, it is.
It is.
Right? Same correction factor. I've got to correct that. Do I have to correct my pressure differential? No. On the distributor, I don't. That's kind of cool.
well, because you're not in a liquid state.
Do what?
It's because it's already changed state, right?
Because it's not experiencing the full pressure drop.
Yeah,
I'm already coming out of my TXV. I've already came out.
yeah.
Right? Does that make sense?
Just taking it from the end of the TX.
Right. And that's the only reason why I get a pass on this one, because it's already happened. Right? But the liquid temperature does matter. All right? So I do need to calculate that.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.